Here are two skylines. Have a good look at them. And can you tell me what skyline fits this silhouette the best? Take all the time you need. Just pause the video if you need some more, because we are about to begin. Jeran Campanella and friends traveled all the way to the beaches of San Diego to capture evidence for a flat Earth and prove their beliefs once and for all. Jiren made his endeavors public and transparent, and he did a livestream beforehand where he laid out his expectations, hopes and predictions for both a flat Earth and the globe. Despite our differences in our opinion on the shape of the Earth, how to avoid bias, and our style of communication, I can only admire his dedication and efforts. It's always nice to see somebody go out and explore the planet. I'm also pleased to know that they had good weather for at least 2 days and that they captured enough footage to indeed settle this debate for good. On the 14th of April, the day before the action was going to happen, Jeren introduced the project during a livestream on Globebusters.
And welcome everybody to Globebusters. Sunset tomorrow at 7:30. It gets earlier than that. Hoping some people show up with a P900 so that we can put it next to my infrared P900 and at least see the differences there. If in case we can't see, or in case now it has been raining the last 3 days, which is good because usually when it rains it gets rid of the marine layer. Let's hope that's what happened, but can't guarantee it because it's going to depend on how the first day goes, where we go for the second day. So really what we're trying to see, or what I want to see, is I want to see San Clemente Island from right here in San Diego, somewhere called Coronado's Cays Park. Down here you'll see this says California State Park building. So we're going to start in this parking lot. If we want to know what direction we're looking at, we're going to look right past this little alcove right here. You'll see this little pop out here. If we go right by that, then that takes us right to San Clemente Island. Now, if you look, that distance is 77 miles. Okay.
So for their first attempt, they were going to travel to a fork in the road of Silver Strand Boulevard, just south of a lifeguard hut tower, number 1, nearby the Coronado Cays. The exact locations are on screen. And in fact, they did go to that area and were filming around to show this to the world. They were about to film San Clemente Island, in front of a setting sun. According to SunCalc, an online sun calculator, the middle of the sun hits the horizon when the sun can be seen in a direction of 282.52 degrees. That's northwest, roughly. Time and Date, an online tool that is very practical for a lot of things, tells us a heading of 283 degrees, so the same but slightly less precise. Stellarium, a powerful star catalog, predicts 282 degrees, 34 minutes and 31.9 seconds. This means that we have now 3 sources that all agree with one another on the direction of the sunset, about 282.5 degrees. According to Google Earth, San Clemente should indeed be perfectly in line with this sunset, so congratulations on the team for picking a perfect viewing location for the 15th of April. Now when we plug in this location in Peak Finder, we again get a prediction for a sunset, 282.5 degrees. Now Peak Finder gives us a blank horizon, as you can see, and so does U-Dorsal, and so does Peak Visor, and also Bart's Ray Tracer. They all calculate the predictions for a globe. So I think it's fair to say that the entirety of the island should be behind the horizon if we assume the Earth is a globe. And if you are a flat earther and you want to be absolutely sure about these predictions, well, listen to this.
There's no reason at all that we should see the sun set behind that mountain. You shouldn't see it if it's a globe. If it's a globe, it's behind the mountain. You shouldn't see it at all.
Alright, now that we know that Jeren actually agrees with the predictions, let's move on. There aren't that many flat Earth predictors out there, and the ones that do exist are actually made by people who don't believe that the Earth is actually flat. But nonetheless, we can use them. U-Dorsal, for example, gives us a nice view of the entire San Clemente Island, from China Point here on the left to Northwest Harbor on the right. This is, by the way, under the assumption that there is no refraction happening in the atmosphere, so that light travels in straight lines. And here is Bart's simulator results. Kind of identical. One final source of information agrees with these predictions. Let's again see what Jeren has to say about it.
If you do the angular size of it, which you can go to like an angular size calculator. So we want to figure out how big in angle would be Mount Thirst from where we're at. And we calculate that and we get 0.27 degrees. So that's about half of the sun. We should see that mountain at half of the size of the sun or moon at the horizon if the Earth is flat.
So if the Earth is flat, Jeran expects to see the entire island from top to bottom, the full quarter of a degree. That is half the angular size of the sun. Now looking at U-Deutschel, we find a horizontal scale. That's the same scale in Bart's prediction. And when taking that scale and placing it vertical too, we can measure that the island is indeed around a quarter of a degree in angular height. So, with all these preparations behind us, we know that Jeran agrees with all of these predictions. The sunset will be in perfect alignment with the island. We expect to see a straight horizon if the Earth is a globe, and if the Earth is flat, we expect to see the entire height of the island visible in front of a setting sun. So, what did they actually see? Jeran and Gru observed exactly what Jeran expects if the Earth is a globe, and not at all what he expects if the Earth is flat. So in a way, their mission is already successful. But let's not forget that Jeran is a flat earther, and flat earthers, they tend to ignore the evidence that proves them wrong. So what is his response actually? Well, Jeran claims that the sun was setting too much to the left.
We expected the sun to set right, well, the right side of the island should be lined up with the point. And so we were looking in this region, but the sun set to the left of that boat. So the sun came down left of the ship there, like out here. So we didn't get any of this lit up.
But that's weird, because as we just saw, all these predictors agreed with each other on the direction of sunset. And Google Earth, U-Deutschel and Bart's ray tracer all place the island in front of a sunset, just behind the curve of the Earth. Could it be that Jeran on Sunday, the day before he falsified his own beliefs, was thinking clearly, making accurate predictions that are reasonable and thought out well, and that Jeran on Monday, who was confirming the Earth is not flat, had difficulties accepting this reality and therefore fled into excuses and ad hoc explanations? Maybe we can actually verify where the island was, using their footage. And what's up with his boat?
Let's hear what Jeran has to say about where the sunset was.
But the sun set to the left of that boat.
Great, so we know it was to the left of the boat. Let's stitch two frames from the footage together. One that shows Point Loma, it's that piece of land on the right, which is this peninsula right next to San Diego, and one with the general area where the sun has set, so that we have all this in a single image. Now let's compare that to a simulation I've prepared. Sure enough, when we align the images using the shape of Point Loma, it puts the sun to the left of the boat, and right where the island is below the horizon, as you can see in this semi-transparent render. But with only Point Loma as reference, the alignment might not be very precise. We should probably use something else too. The only other available thing seems to be the boat, so let's use that. The first suspect is Coast Guard ship Stratton. Here it was during the sunset, almost exactly between Point Loma and Jeran's observation spot. It looks like a good candidate, so let's put it in a simulation. We can find on the internet that the ship is about 43 meters tall, so making its image to scale we get this. Okay, that's not good. The position and size don't match. But would you look at that? This footage taken by someone from Jeran's group actually clearly shows Stratton sailing to the side, while another ship, it's the one we are interested in, remains in the same position. So it was not Stratton. Some searching later, and with some help from Ole, I found this ship. It happened to hang around this location during the sunset and a few hours afterwards. I haven't screenshotted it on marine traffic though, and the website won't let me see history older than 1 day. Unfortunately, as I'm recording this, it's already almost 3 days after the observation. So if you want to verify this independently, you might need a paid account with marine traffic. And even that might not be sufficient, as this is a government ship. Sorry. Anyway, this ship is also about 40 meters tall, and putting its image at this position creates this simulation. Awesome. We now have great alignment, and the size matches too. So that should give us a bit more confidence in what the simulation shows. And what it shows is also a direction of the sunset matching Jeran's words, and that the sun set in the direction of the tallest part of the island. Only Jeran wouldn't see any of it because it was below the horizon, because, you know, the Earth is round.
Fair enough. Jeran confirmed last Saturday that he was indeed in the correct spot.
I guess I still got to look into it because I think I expected the island here, but I think that we actually were right. It was somewhere to the left of those ships, according to Wolfie.
But it should be said that he needed help from another Globie to avoid his own bias. It almost sounds as if Jeran is desperately looking for excuses for why they didn't see the island. Good that we double-check his work, isn't it? Remember that I said that there are no flat earthers building flat earth predictors? Well, what about Flat Earth Dave's app? And Jeran is promoting it on Globusters, so it means something to him at least. As Flat Earth Dave will tell you, his data matches the data from Time and Date. Not really a surprise, they both use the same data that is coming from the heliocentric globe Earth predictions. So we can simply use Time and Date and don't spend any money on Dave's grift. For the time of sunset, we need to use the UTC time of 2:17 AM on the 15th of April. This gives us a ground position, or GP of the sun, on this exact location. Now, using SunCalc, we can even fine-tune this value by clicking around until the elevation matches 90 degrees, and that is at this exact spot. If we now draw both our location of observation and the ground position of the sun, we can get an azimuthal direction towards the sun if the Earth were flat and shaped like the polar azimuthal equidistant projection of the globe. The projection that Dave uses to fool his audience. And we get an angle of 310.39 degrees. Oh, but look, I just received a screenshot of Dave's app for the exact time of observation. And would you look at that? It is indeed a perfect match. But we can't just apply the sunset angle on our previously rendered panoramas, can we? Because not only the position of the sun is different, the entire terrain needs to be remapped. If only we knew somebody who can actually generate a panorama using a polar azimuthal equidistant flat Earth.
As it happens, my ray tracer can do that. I can set it to not simulate any refraction like the flat earthers prefer. This is the prediction when we use the globe, but flatten it around the observer. While this is what you get when you map the terrain onto a model based on the usual flat Earth AE map, similar to how Dave shows flat Earth in his app. The azimuth to the sun at the time of the sunset we just calculated would put it out of this frame, somewhere to the right. Wait, behind Point Loma? Not over the ocean? Or no, not really. With the height at which flat earthers put the sun above a flat Earth, it would actually be somewhere here. Yep, not even close to setting. That's what happens when you put the sun 3,000 miles over the surface. Of course, flat earthers can't agree about the height of the sun, but unless they place it at an altitude on the order of magnitude of that of airliners, which is absurd in its own way of course, they won't really get anything like a sunset. Well, too bad.
Now I start to understand why flat earthers are hesitant to give us some flat earth values. Their consequences don't really stand up to scrutiny, do they? Now, after Jeran declared that they were in the wrong position while they were actually not, his team moved to Point Loma to seek higher ground. This was something that Jeran already mentioned in his preparation speech and something I suggested him multiple times.
The other thing I want to see people do if they can is from this spot, if somebody wants to meet us here or whatever, but I want somebody to come over here. And there's some great spots up at the top of this hill.
New day, new chances to prove the globe right. This time they were on this spot here. Cameras were rolling and at that time I was burning with anticipation. What would they be seeing this time? Then a message came in. This was awesome, time to eat crow, Roofy. That's Ruhef, who was actually chatting with them and helping them out with their predictions. Mission success. Shit's flat, everybody. Hella flat, but we knew that already. Total win, there is no debating this. We saw the whole island. Well, again, as Jeran pointed out on Sunday, if the Earth is flat, that's indeed what he expects to see. From his viewing spot at Cornish Drive parking, this is the panorama for a flat Earth where no refraction is happening. The island spans from an azimuth of 275 degrees to 287.5 degrees. A sunset was expected in the direction of 233 degrees, so again behind the island. Although there isn't a perfect alignment with the highest peak, Mount Thirst, the sun should most definitely have set behind the island. Although the higher terrain is about 3 or 4 degrees more to the left. So, what did they actually see? Okay, I have to admit, that's very cool, and I'm glad that they went out to higher grounds and were lucky with the weather. What we can do is stitch some frames together to get the whole visible silhouette in one shot and compare it with the expected silhouette for a flat Earth, which is not really a match, is it? The observed silhouette is way more pronounced, while the rendering is kind of boring, without that many ups and downs. Let's add some curvature to the Earth, shall we? And when we make the Earth more and more curved, we see that the horizon obviously starts to cover the base of the island. And if we stop around here and then zoom in, it looks way more like the silhouette from the actual footage, don't you think? But that means that most of the island sinks behind the horizon. About 1,800 feet is gone. But Jeran doesn't believe in a globe. His main reason seems to be that downwards refraction is required to match this observation with the given radius of the Earth. But how do we know that this was actually the case? It's not because it's possible that it must have been the situation while Jeran was there. How can we falsify such a condition? How can Jeran disprove the globe when we can just say refraction as an answer to every outcome? If he hadn't seen the island entirely, we would have cried victory. If he saw the highest 80 feet of the island, we would have cried victory too. And if he saw half of the island, again, we would add a little refraction and call it globe Earth evidence. Now, to be clear, this is not my position. It seems to be how Jeran interprets what we do. Jeran doesn't like refraction as an explanation for the globe because it is a variable. It's constantly changing. And because it's constantly changing, he argues that it is constantly an excuse for whatever outcome there is. But Jeran believes that the Earth is flat. And as we have discovered, the observation does not match the prediction for a flat Earth. Even the prediction that Jeran himself made. So what is his explanation for why 90% of the island appears behind the horizon?
Start to pay attention here. We see a water line, hard water line here. And we see a water line here, but the boat is clearly traveling on the water back here. But you'll see here, you've got boats that go up till they hit this peak, and then they begin to level off, and then they travel on a flat plane. However, that flat plane is probably up around your eye height. At which point, can you see something flat at your eye height? That wouldn't make sense. But if something is traveling away from you, flat on that eye line, it's going to get smaller and appear to kind of morph into the horizon.
Look at this right here. You can see, from me zooming in here, that the ground is getting distorted. And that is the mirage effect happening. Take a look, is right in here. I'll start panning it in. And you can see the mirroring effect already taking place. Everywhere where you see a thing at the bottom, there's also that same effect.
So his first reason seems to be refraction in the atmosphere. And he shows a lot of examples of what we call an inferior mirage. Now, what do we need to get such a phenomenon? Light refracts from the less dense medium into the more dense medium, or more technically, from the medium that has a lower refractive index towards a layer that has a higher refractive index. Both the air pressure, the temperature, and the humidity of air influence the refractive index of the atmosphere. So when we have a hot road, for example, the air sitting right above the hot road is way warmer than the atmosphere a bit higher up. So what we do have here is a rapid decrease of refractive index. The higher you go, this means that light is bent upwards. And when this gradient is so extreme, it can happen that the light will not go through this gradient, but it comes out again the side that it actually entered this gradient. When light comes from above and it enters this gradient and it is refracted upwards, it can hit the eye or the camera, and what you will see is what is actually above this density gradient. And what you will see is when we add an array of lines of sight, you see that these bending lines cross over one another. And this will result in a flipped image, very similar to what we see happens in a real mirror. So that's why your brain will interpret a mirage as something that looks mirrored. When your line of sight here is too steep, there isn't enough room to actually make the entire bending up, and it will hit the ground before it can actually bend up and show the sky. So that's why there is this hard separation between what looks like an illusion of a horizon. So these inferior mirages, they will in fact lower the observed horizon. And above this observed horizon, you will always find a flipped image of what is above the mirage. This can also happen during a sunset, where after a hot day, a lot of the water is evaporated, and moist air with a lot of water vapor, actually acts like hot air. So it doesn't need to be hot, but the vapor in the atmosphere will actually also decrease the refractive index. And therefore, light that is coming from the setting sun can actually refract, and instead of going into the water, will actually hit your camera or your eye. Most of the time this is actually a very small, a very thin layer right above the water, but it gives a very nice reflection here. Looking at Jeran's sunset on day 2, we actually don't see that this effect is happening. And when we have a look at the island itself, we actually don't see any flipped portion here. So it's very strange that Jeran actually argues for an inferior mirage, while he himself tells us that this is not the case, and while the sunset prior to his observation shows that this was indeed not the case. But he has a second explanation.
Am I saying this is the whole mountain? No, I don't think it is. I don't think that we see all of the buildings in Chicago. But we know it's not a mirage. Okay, mirage is when you have a repeating, an upside down image. We don't see any of that here. There's no mirage here going on. At least the mountain isn't miraged. So if there's no mirage, then what are we seeing here? We're seeing a flattened, condensed mountain, and we're seeing something that the globe I just got done showing you says doesn't exist.
So his second explanation is yet again a refractive phenomenon. This time it is compression. So what we can do is take the image, the expected image of the island, place it in front of the sun, and then use the displacement that we can see in the sun to see how the island will be influenced. And this, as you can see, does not give us a match with the actual observation. So I don't think that compression here, again, is what Jeran needs. Now, as a third explanation, Jeran argues yet again for another type of refraction. This time it's a superior mirage, but he doesn't come up with that name.
Well, if this is miraging, meaning that this is mirroring what's in front of it, then really the surface of the ocean is here. Now, here comes this boat. Well, it's also on the surface of the ocean, meaning the surface of the ocean is here. And this boat is just going to come in. It's staying at the surface of the ocean, staying at the surface of the ocean, staying at the surface of the ocean. So all that we're seeing is what they call a hump is simply a mirage. It's funny because I started every show I do with, it's not a mirage.
Now what he's arguing for is that we have a layer of reflected ocean. So instead of having a layer of refracted sky or sun or car, we now see the ocean higher than it actually is by flipping the image. But what this requires is the observer being below a rapid change in refractive index. This time what we need is, for example, a layer of cool air, and on top of that a layer of warm air. And again we need a gradient that is so steep that light will not go through, but will actually be bent down back to the surface of the water. Or in the case of Jeran, back to his camera. And just like these other examples of inferior mirages, we expect to see an actual flipped image of what's below. So what we need is these wave patterns being recognizably flipped higher up. Now I have to say that this is a very creative idea, and I think that this deserves a separate video on its own. It does indeed create a rather straight line at the top of the miraging effect, but it's weird that in none of the footage we actually see signs that this is happening. Now let's go back to the globe, because what does the globe actually need to have a slightly more downwards refraction to make the Earth appear slightly bigger? Now, I can make a near perfect match with a refractive coefficient of 0.21. This means that if we have a temperature at sea level that is 1 degree lower than a temperature at the top of the island in Celsius, so just a gentle rise in temperature of only 1 degree over 600 meters in elevation, that's already enough to actually give us a refractive index of 0.21. On the other hand, this means that a flat Earth needs a refractive coefficient of minus 79. And to get such an extreme amount of upwards refraction in the atmosphere, the temperature needs to drop by 81 degrees Celsius over this 600 meters rise. That means that we need freezing temperatures 60 degrees below freezing point at the top of the island, half of April, in California. Now the good thing is that right in between Jiren and the island there is a buoy, and that buoy was actually measuring the sea temperature. And 2 hours before Jeran made his observation, there was an atmospheric sounding performed above San Diego. And as we can see from these two measurements, it's very clear that the atmosphere at a couple of 100 meters above Jiren was a couple of degrees warmer than the temperature of the ocean. So a temperature rise to give us slightly more refraction than average was actually measured on the day of observation. In fact, this temperature inversion was already predicted the day before he made the observation, and we took a screenshot from that. Here in the lowest part of the graph you can see that this line is going to the right with elevation, meaning that the temperature is rising and then again dropping. And this temperature inversion, which was actually also measured half of April last year, is what gives us this prediction that on a globe we are actually supposed to see the peak of the island. In fact, I would be very surprised if we had not seen it. If we input this graph here, that is based on the measurements performed 2 hours before Jeran made his observation, if we plug those values into Bart's ray tracer, which actually traces the path of the light through this atmosphere on a globe, this is what he expects to see. What is it, around 100 feet of the top of the island.
Now, let's take a break here and think about this for a second. What if it was not Jeran but me who made very clear predictions? Like, for example, if the Earth is a globe, we will not see the island, none of it, not even from 80 feet in elevation. What if that was the case? And then Jeran went out and actually saw the tippy top of the island. What if I then made a 3-hour stream talking about all sorts of refraction to explain why we actually were supposed to actually see it? What would Jeran's reaction be? He would be pissed. He would say like, see, you are just throwing refraction at it and then see what sticks and then, explain after facts. But that is exactly what Jeran did. He made very strong predictions that he was going to see the entire island and he was very convinced about that. Then he saw only the top of the island and then he tried to explain with all sorts of refraction how this observation was actually possible if the Earth is flat. The interesting thing is, though, that I did make predictions. A month before the observation, I shared with Jeran my predictions. And I took data from the year before in the same period. And I said, we have a temperature inversion. And if that happens, we can actually see a little bit further than we normally do. So I expect we don't really see the island unless there is again one of those temperature inversions. And then I explained to him what influences that the temperature actually has on the observation. And I laid out everything to him. But his reaction was simply that he already denied all of that before the observation was even made. And as it turns out, afterwards, my predictions came true because there was a temperature inversion. So right now, Jeran is accusing me of doing something that I actually did not do. And he is accusing me of doing exactly what he is doing. So I don't think that I follow why he's so angry at me. Maybe it's because the evidence proves that the Earth is a globe. Who knows?
So, is there a final way to verify this all?
All right, so here's a screenshot from Jeran's infrared video. And as you can see, I've had to rotate it about 2.6 degrees clockwise so that the horizon was horizontal. And then I've drawn a line across where the horizon is. And a really simple way to work out how much of this island is visible is to use that radar on the right-hand side of the island and just scale the height of it against the terrain that's visible above the horizon. Now, you guys can go and measure the pixels if you like, but on my PowerPoint slide, the little blue tower is 80 millimeters high and the green one is 90 millimeters high. And by the way, there are actually buildings at the base of the tower that are probably 10 feet tall themselves. So I think I'm being generous. I could quite easily make the blue one 90 millimeters and the green one 80 millimeters. And then there'd be even less terrain visible. But anyway, let's stick with the blue one at 80 and the green one at 90. So this means, for example, if the tower itself is 40 meters high in reality, then the amount of the island visible would be 45 meters. Or if the tower is somehow 80 meters high in reality, then the amount of visible land is 90 meters. Pretty simple stuff. But how high is the tower? So my first port of call was to look up the FAA obstacles database, which lists all the things that pilots need to look out for when they're flying around. And here's what that file looks like. It gives you the latitude and longitude of the obstacle, and then over on the right, it's got the height above ground level and the height above sea level. So the FAA, of course, uses freedom units, and they have it listed as being only 90 feet tall and 2,054 feet above sea level. And if you subtract one from the other, you get the elevation of Mount Thirst as 1964 feet, which matches what Google says. So that's not a good result for Jeran. If the tower is only 90 feet tall, then applying that ratio that we just derived from the screenshot, that means there's only about 100 feet of the island visible. And I'm sure that's devastating. So let's see if we can give you a few more feet just to make you feel better. Right, so I managed to find this really nice square-on photo of the radar that we can use to try and get a height. If we can work out a diameter for the radome, then we can just scale that against the height of the tower, and voila, we'll have a height. But getting a diameter for the radome is a lot easier said than done. So I ended up going into the Google Earth historical views and trying to find the roundest and highest resolution images and basically taking an average. So I got images from 2013, 2015, 2021 and 2023, and the average was around 8.5 meters. And that makes the diameter of the radome 17 meters. And if we scale that against the height, then we get a total height for the tower of 34.6 meters, which is 114 feet. So, Merry Christmas, Flurflings. If we use that ratio that we derived earlier, then you can now see 128 feet of the island. Congratulations. But I had another idea. We could use the length of the shadow that the tower casts on the ground to work out the height. Now, this is something I did several years ago to work out the height of some wind turbines that my good friend Jay Tolan and I were arguing over. And I'm sure it's no surprise to anyone that my calculations turned out to be correct. But there are two very tricky things that you need to take into account when you're doing a shadow analysis. Number one, you need to account for the fact that the tip of the shadow may not be landing on ground that is the same elevation as the base of the tower. And the terrain around Mount Thirst is quite steep, and Google Earth elevation data tends to be fairly unreliable when the terrain is steep. So that's why I chose this imagery from July 2023, where the tip of the shadow falls on level ground around the tower, rather than being cast onto the sloping ground. The second thing you need to be really careful with, especially with something so wide, is where exactly on the ground is the base of the structure. So a lot of these satellite photos are not taken from directly overhead, they're taken from the side. So the image that Google then overlay onto the terrain map doesn't quite match reality. So in this case, in the image, the red dot is the center of the radome, but because of the way the image has been overlaid onto the terrain, that spot is too far to the right. So I had to figure out from other aerial shots around about where the center of the radome is in relation to stuff that's much closer to the ground. So you can see where the tip of that green line is in relation to the nearby buildings, and that's the point on the surface where I think the center of the radome is on top of. And that corresponds to this green line. So I think the center of the radome is between those two rectangular air conditioning unit looking things. So what I did in Google Earth then was measure the distance over the ground between the tip of the shadow and that green line, doing my best to keep it in the middle of the shadow, and that came out to be 18.85 meters. And guess what else we have? We have the heading for the direction to the sun, which is 112.48 degrees. And down the bottom, we also have the date the image was taken, which was the 4th of July, 2023. So all the non-flurfs can probably guess what we're going to do next. Well done. We go into Stellarium. We set the date to be the 4th of July 2023. We set our location to be the radome on Mount Thirst. And then all we do is play with the time until the azimuth to the sun is 112.48 degrees. And when the sun had that azimuth, we also know the elevation angle to the sun was 68.6 degrees. Right, so now I just want to shout out a YouTuber who goes by PT194. He is legit the GeoGebra king. He can do far more complicated stuff than I've done here. So PT194, PETEY 194. I don't think that this diagram needs too much explanation. I've modeled the radome that's 17 meters in diameter. I've made a shadow that is 18.85 meters long, which is what I measured in Google Earth. And then the yellow line is obviously the rays coming from the sun, hitting the edge of the radome and causing the shadow. So all I had to do then was adjust the height of the tower until that elevation angle matched the elevation angle of the sun, which was 68.6 degrees at the time of the satellite photo. And you'll see that I get 68.6 degrees when the tower is about 33.4 meters tall. And for all the Americans out there, that's about 110 feet. And I think that's an excellent match for the 114 feet I got earlier with the photo. Right, so let's get back to the screenshot. Remember the blue rectangle was 80 millimeters in my PowerPoint slide, and the green one was 90 millimeters, with a tower measuring 114 feet maximum. And we scale that against the green rectangle, then that makes the amount of land visible a pitiful 128 feet. And if Mount Thirst is 1,965 feet tall, then the amount hidden by the horizon is a whopping 1,837 feet. So if you want to claim victory when more than 90% of the island is below the horizon, then go right ahead, I guess. Back to you, Tom, with the weather.